In this video, I'd like to continue talking about the electronic structure of transition metals and look at some periodic trends in oxidation states. So I have a few graphs here pulled from a few different textbooks that I've taught from throughout the ages. And they're really trying to compare our transition elements in terms of a couple different of our periodic trends that we track. And so right here, we've got size. We've got ionization energy at the top, and we have electronegativity on the bottom. So for our size trend, starting there, looking at it, we can see that our size in general, we're showing here going across each of these dots right here, are going across the periodic table left to right. And as we go across the periodic table, we see our size decrease. This fits our general trend that we have of seeing size decrease as Z effective, the effective nuclear charge that electrons on the outer shell are experiencing increases. And it's increasing with a greater number of protons. However, the same number of electrons in that outer shell, or the electrons are at the same distance. And in the terms of the transition metals, we're not adding electrons into this outer valence shell, we're adding it into the core of the electron. And so we still see our normal size trend in general as we go across, especially here at the beginning where we see size decreasing. But then we really see that trend level off, and we don't see much change across the later half of the transition metals, especially for the first row. And if you look at the second and third row, you actually see a little bit of an increase instead to our size. And so as we're increasing that Z effective right across the periodic table, we're also, in the case of the transition metals, we're increasing the amount of shielding. We're adding more of these core electrons in. And so those outer sphere valence electrons, of which there's only two, as a proton's added, another core electron is added. And as another proton's added, another core electron is added. And so there isn't a huge change in that Z effective that is actually experienced by those valence electrons. And when we talk about these second and third series, then we're also then adding an entire other subset of core electrons to it, which is the f orbitals. So now for the second and third series, the 4D and the 5D block, we're going to have, or for the 5D block, we're going to have the lanthanide series in there as well. And we actually see something called the lanthanide contraction, which is because there's so many more core electrons populated into the atom that we see that effect of the nucleus on the energetics of the valence electrons decrease. Like that attraction has more in the way between them. And so we see this kind of difference in our size trend, this leveling out at best, and actually a slight increase. Looking at our ionization energies next, we see those first ionization energies increase as you go across the table. And I'd like to highlight this part of the third ionization energy right here for manganese and iron, that we see this increasing trend that stops and then decreases. And this is really looking at the third ionization energy is the ionization, the removal of one of our d electrons finally. So if we lose both of our s electrons first, then losing a d electron is going to be more energetically costly for something like manganese that has a half-filled set of d orbitals. And so removing that electron from the d orbital actually loses that stability that comes with being half-filled. And it's easier to remove that electron for iron because it has 6 d electrons. And if it removes one of them, it actually becomes half filled. And so it actually gains some level of stabilization from that. So it's easier to remove a d electron for iron than it is for manganese. Now, looking at our electronegativity chart for our first row here in blue, you can see that it increases a little bit as we go across, and it kind of levels out and dips for our first row right at the fifth position. And then again, that fifth one, that's when we have a half filled d orbital right here. We see this kind of dip across the board. And then a slight increase in leveling out again. And we don't see a very large change across the periodic table within the transition metals. And it's a possibility that this third row is kind of the exception, that we have an increase up and then a drop. In all cases, we see this drop here at the 10th one because we have a filled d orbital and we have a filled s orbital. And so there is less energetic savings, I guess, to populate just one electron into the p orbital, rather than just stay completely filled d and completely filled s orbitals. I also wanted to stop and talk about transition metal oxidation states a bit more. And I think that this is one of the most interesting things about this group of elements, is that they have the ability to occupy so many different oxidation states, which allows them to undergo some really fascinating reduction and oxidation chemistry. And so we have a couple of different versions that list these, and my preference is actually for the lower one right here. And so we have a list of the common oxidation states, and here we do as well. And so for these ones, our most common ones are the ones that are circled in white, and I'm going to highlight them in blue. And these are going to be the most common oxidation states for each of our elements in our first row of transition metals. And then the other dots that are already filled in red, those are the ones that are going to be less common, but very possible. And so you can see, looking at this, it really gives you a sense of anything is possible for a lot of these elements, especially for these ones in the first half of our periodic, of the first half of our row. The ones that have half-filled d orbitals have more flexibility in those oxidation states because we don't have spin-paired electrons, which are occurring then in the second half of the transition metal row. And we see in general that within our transition metals, that first row is more reactive, and we see more possible oxidation states available to it. We'll see then with our second and third row transition metals that they have a little bit less reactivity. We also generally see that the higher oxidation states are more stable. For things that have the d electrons a little further out from the nucleus. Further out there, the more stable we can get those high charges on the metal atom themselves, and they're just a larger molecule in general in terms of its size. And so that's kind of an interesting trend that we see as well. So don't worry about memorizing these common ones. I think, if anything, I'd like you to walk away from this with this sense of awe and that anything is possible, which is, I think, exciting about it, especially like with iron. Well,